In the last lecture for this week, we introduced a very interesting concept of random hash. It is a concept which is typically taught separately, not along with this, not here where we are introducing a measure of uncertainty. But I think it's rightly placed here because it's a very basic concept and should be introduced upfront. So let's revisit our question answer paradigm. So in our the way we were formulating that problem, the compression problem and the questionnaire and answer problem, there's a person who's trying to who was asked a question. It was, let's say, you when you're trying to when someone raises a question to you, and the this person already has a list of guesses. Okay, this list L, and here is a person who actually knows the correct answer. So I'll make them okay. This X and this X. This guy knows the answer, and it has to describe this answer to you. And what we said was that instead of just making a list like this, uh, you can think of a model on all the answers. So that's this distribution P, where Px is the probability with which this answer is X. And that's the model P here. And now this list actually corresponds to the set A lambda we saw last time. It's the set of likely answers which you can form. And when we previously described this formulation, here we assume that this person describing the answer here also knows P, okay, and also knows this list, and therefore it can arrange the answers according to this list and give you that answer. Okay, and in that paradigm, what we show is that you can always form this list of size approximately 2 to the power h of P, such that probability that your answer belongs to this list is greater than 1 minus epsilon. A significant probability that you will have a list of this size and that answer belongs to this list. That's what we saw. You can. So the important point is that the size of list can be this one here, 2 to the power hp, right? And therefore, to describe this answer, you need only hp bits because there are these many answers. This is roughly what we have seen till now. But it's very important to notice that this requires both. So this is the answerer here. Okay, this is the person who's giving you the answer to the question. So I'll call it the answerer. So this person also knows P, the same P. And it also knows this list that you are forming. Requires the answerer to know P, the model. However, what can we do if this answerer doesn't know P? And this is exactly what random hash will be able to. This is exactly what a random hash will be able to do for us. What a random hash will be able to do for us is that the answer gets still send these many bits about the answer without knowing P. This is very important, without knowing P. Okay. And the person who's trying to guess, who has formed this guess list, gets the answer with large probability. So that's what we'll be able to do with a random hash. So let's introduce a formal notion of random hash. So here is a definition. An L bit, L is a number here, a natural number. An L bit random hash is defined as follows. We consider a random function f from your alphabet to all functions with L bit output. And it's a random function. What is a random function? Random function is the one which is chosen uniformly over the set of all such functions. How many such functions are there, by the way? So you have to express 2 to the power L outputs. Each element in X can be mapped to any such output. Okay, so you have 2 to the power L choices for each element of X. You multiply them, and so that gives you this. Okay, so there are so many such functions, a large number of functions, and fx is chosen randomly over that. Such an fx is called an L bit random hash of the input X. So we will observe a very interesting property of this random function, which is called a collision resistance property. Okay, it's very easy to state. What it says is that for a random function f, which is just randomly chosen over all functions, if you consider two distinct elements x and x prime, then the probability that this random function maps both of them to the same value is very small. It's 2 to the power minus l. Remember, this is a random function f from x to l bits. So it's an l bit random function, and this l is what shows up here. Okay, so you can show this. It's not a difficult exercise. You can show that for any fixed x prime, this is the probability of hash collision. So what this observation tells us, and then when this L is, let's say, 100, this probability is very small, 2 to the power minus 100. Okay, so 2 to the power minus 100 is an extremely small number. You can convince yourself about it. Just with 100 bits, you can have this property, which is called the collision resistant property. Therefore, in English, what we have just shown is a random hash is an almost one-to-one map, in the sense that the probability that it maps to different elements to the same value is extremely small, 2 to the power minus l. Alright, so we will use this property of random hash to answer the problem which we raised earlier. So suppose now the guesser, the person who is trying to guess the answer, has a list A, okay, of guesses of answers such that x belongs to A. Instead of saying that it holds with large 1 probability 1, let's say that the unknown answer x belongs to A with probability greater than 1 minus epsilon. Suppose that holds. Okay. The answerer who was earlier describing the location of this x in this list, which it can do because it knew the list, now it doesn't know this list, but it can still send this random hash fx of this input x. So it just computes it. Suppose it can be computed efficiently, so it just computes it and sends it. Okay. So once again, just to draw some picture, there are these two entities here, answerer and the guesser. Okay, so this guesser has a list A, and this guy knows the answer, and it sends to the guesser f of x. Claim is that this f of x will allow the guesser to recover the answer with large probability. So what the guesser can do is it can declare the answer x hat as the x in this list A, okay, for which the hash of that element x matches the hash received from the answerer. So the answerer has sent some hash value to it, and this guy goes over all its elements x prime and look for that element for which the f of x prime matches the fx received from the answerer. And if there are multiple such guesses, you take any one of them. So how good is this guess? So we'll show that actually this guess is accurate with large probability. We'll try to bound the probability that this guess differs from the actual answer. So if you look at this probability, you can divide this into two parts, two events. This is the total probability formula. The event that the actual unknown answer lies in this guess list, and the event that it doesn't lie in this guess list. So this is an intersection of these two events. X hat is not equal to x, and x doesn't lie in the guess list. So it can be bounded by the event that x doesn't lie in the guess list. But this we assumed this guy is less than equal to epsilon. So the second term here is less than equal to epsilon. Now how about the first term? Well, I can write it as probability x hat not equal to x given x in A times probability x in A. But probability x in A is bounded by 1. So this term, the first term, gets bounded by this guy. Okay, probability x hat is not equal to x given that x is in the guess list. So let's try to analyze this probability now. Probability that x hat is not equal to x given that x is in A. How do we analyze this probability? So let's try to write it completely. So this is the probability that, so 1 by probability x in A, I'm using base rule here. Okay, and I'll sum over all x in A, and this probability then becomes probability that x hat is not equal to x and x equals to x. This is exact equality. But this can only happen if f of, so when can this thing happen? The answer was in A and this guy had sent this answer. So this can only happen if there is some other x prime. Okay, so there you can find some x prime. There exists, the symbol is there exists, x prime not equal to x, such that x prime is in A and the hash has the same value. Only then this kind of thing can happen. And therefore, there are at most these many cardinality of a such x prime. And for any such x prime, the probability of hash collision is 2 to the power minus l. Therefore, you can show that this probability here is bounded by this quantity here. So I'll give you the proof details in the notes when I'll put them up. And I want you to try this bound, but I gave you the main idea behind the bound. You can show that this first term is bounded by the size of the list times 2 to the power minus l, your hash length. Okay. Therefore, if you combine all the bounds, what we have shown is that the output differs from x with this much probability, epsilon plus a to the a times this. If we choose, now this L is something we have to choose. You have to choose the length of the random hash. Okay. By the way, we can choose this A to be that L epsilon P thing. And then if you have a random hash, this bound becomes this. And if you choose this L, the length of the random hash, to be greater than L epsilon P plus 1 by eta for some parameter eta, then this bound becomes 1 eta plus epsilon. So for instance, if this is 10 to the power minus 6, then you have another 10 to the power 6. Then you have another, so this is, by the way, log 1 by eta. Yeah. So then you have log 10 to the power 6, which is just 6. So if you choose L to be greater than this, then this probability of disagreement becomes small. Okay. So what is the conclusion? The conclusion is that the answerer didn't actually need to know the guess list. All it need to know was that what's the accuracy with which you want to match the answer. And with that, it can actually use a random hash of appropriate length and send a hash which will give you reliable recovery with high probability. Okay, so you don't even need to know the answer P, the guess list to give the answer. You can just send a random hash. That's the idea of random hashing. This is a very powerful tool. It's a very powerful tool for practice as well as for theory, and we'll revisit this later in the course. Okay, so as a conclusion of this lecture, of this video, what you can remember is that it's not that the answerer also needs to know the model with the guess which the guesser formed. All it needs to know is the accuracy that the guesser is looking for, and it can send a hash of the true answer. And the guesser who has a guess list, that a lambda which we used in our scheme, it can just go over that guess list and select the answer for which the hash matches the received hash. Okay, that's the conclusion. Alright, that's all for this week. So this week what we did was we related the measure of uncertainty to, we said that uncertainty can be measured as minimum number of bits required to represent a random variable. Then we studied the problem of minimum number of bits required to express a random variable. This is exactly the compression problem. What we discovered was that the fundamental limit of this problem can be measured in terms of this quantity called entropy of this random variable, which has this formula, which is a very concrete formula, this notation HP. And it has a concrete formula, summation over x, px log 1 by px, which you can compute. Okay. And what we claimed was, okay, so this entropy is the measure of uncertainty, and it can be computed explicitly. Some examples we saw, uniform distribution has high uncertainty. Of course, so entropy is also larger, likewise. And a distribution which is more peaky, which has heavy mass at one point, has lower entropy. Has lower uncertainty, as one can expect, and the entropy then also is likewise smaller for such a distribution. Okay. And finally, we saw this notion of random hash, which satisfies this basic property, which we call the collision resistance property, which says that it is a random hash is an almost invertible map. It's very rare that a random hash will map to different elements of the same value. And using this property of a random hash, we came up with a very interesting scheme which doesn't require the answerer to even know the guess list to answer the question. Okay. All right. That's it for this week, and I'll see you in the next week.